Hello, welcome everybody to the Georgia Tech Graph Theory Seminar. Our speaker today is Éva Czabarka from University of South Carolina, and she'll tell us about maximum diameter of k-colorable graphs.
Hello, everyone. Thank you for the invitation. I would like to say that if you have a question while I'm talking, please speak up because I have a really tough time trying to monitor whether someone is trying to ask a question or not. So I'm going to talk about the maximum diameter of k-colorable graphs. And this is joint work with László Székely and our PhD student Ines Singhi, who now graduated. Oh. So it's an old theorem discovered by many people that if you take a connected graph G on n vertices and minimum degree delta at least 2, then the diameter of G is at most 3n over delta plus 1 plus a big O1 term where the big O1 is as n goes to infinity. And this is sharp, as can easily be seen by this example. Take a sequence of complete graphs roughly of size delta plus 1 over 3 each. Every third one is a little bit corrected to make sure that you have the exact number that you want, and connect every vertex to every other vertex in 2 consecutive ones. And at the end, you, for example, can blow it up to a k delta to make sure that the degrees are fine. So Cocetta and Smith have shown that the band above is sharp even for delta regular graphs. The example is a bit more messy, obviously, because what I was doing at the end, blow it up, messes things up. So Erdős, Pach, Pollack and Tuza, quite a bit of time ago, conjectured that you can actually improve this bound if you exclude a large enough click in the graph. So they have said they have made the following conjectures. If the graph, in addition to have minimum degree delta and order n, doesn't have a complete subgraph of size 2r plus 1, and 3r minus 1 divides delta, which is a technical condition that they put in, then the diameter is at most 3r minus 1 over r n over delta plus big O1. There, I want to rewrite this 3r minus 1 over r as 3 minus 2 over 2r. The 2r that I put on the bottom is the maximum possible click that the graph can have under the conditions. And this, if correct, is sharp, as shown by this example. Take a sequence of columns. Each column contains r clumps. Each clump has delta over 3r minus 1 independent vertices in it. And we will do something at the end to fix everything. But vertices are adjacent to each other if they are in different clumps of the same columns or consecutive columns. So that means that if you pick any particular vertex, it is adjacent to the vertices in the previous column, the same column, and the next column, a grand total of 3r minus 1 clumps, because it's not adjacent to anybody in its own clump, and 3r minus 1 times delta over 3r minus 1 is delta, so it has minimum degree delta. The diameter is roughly the number of columns. You work it out, everything works out fine. If the graph is K2R free, so there is a divisibility condition here, whether it's even or odd, and r minus 1 times 3r plus 2 divides delta, then the diameter of G is at most this quantity. And this is the example that shows that this is sharp. Now you don't have the exact same number of clumps in every column, r clumps, r minus 1 clumps. The clump sizes are not the same, but you do some algebra, it works out. I don't even want to go through it because it's a bit more tedious. But I want to rewrite again that quantity as 3 minus 2 over 2r minus 1. 2r minus 1 is not the maximum click size that's allowed, minus a teeny bit more, times n over delta plus big O1. So essentially,
Let
yes?
me ask a quick question.
Yes.
Is there also some kind of natural conjecture in the case where the divisibility conditions are not satisfied?
Anton, do you want to ask that question?
Yep, I'm back. There's some internet issue. Yeah, the question I started asking was, is there some kind of natural conjecture in the case where the divisibility conditions are not satisfied?
I would say that if the case when the divisibility conditions are not satisfied, you can modify what you have.
Mm-hmm.
It's just not going to be reached.
Uh-huh.
It's just going to be approached from below. So
Mm-hmm.
that's not really a strong condition. It's just, you
Right.
know, you can put in a few extra vertices here and there, and then you have something that's not exactly that much, because the bottom,
Mm-hmm.
instead of constant times delta, you will have a constant times delta plus another constant.
Mm-hmm. I see. So somehow maybe instead of big O of 1, and you will have like little O of n term of some sort.
Yeah.
Okay.
So you might be able to have something less for every fixed delta,
mm-hmm.
but your constant is going to be the same if
mm-hmm.
you want something that works for every delta, I would say that.
Yeah, I see. Thank you.
You're welcome. So now this is what we have, and this 7n over 3 delta plus 1 is exactly what you asked. Is 7/3 times n over delta. I did away with the O1 term because I said it's negative. So it is smaller than 7/3 n over delta, but as you make delta bigger and bigger, it approaches. So if you want a constant that works for every delta, 7/3 is the best one you can put in there. And 7/3 is 3 minus 2/3. And this is the case when Erdős, Pach, Pollack and Tuza shaved off a little bit from that 3 minus 2 over k. And in fact, even when delta is not even, you can use the same block. You just have to modify your number of vertices accordingly. And I have done it because you can do it at the same time. So it works both for even and odd delta with appropriate floors and ceilings. So what we have here is 7n over 3 delta plus 1. And it's bigger than the conjectured Erdős bound when delta is bigger than 16. So the Erdős conjecture is not true in the free-colorable case or the K for free case, because these graphs are K for free. But maybe this is just a fluke. So the odd 2r minus 1 colorable case, when k sub 2 are free, if we could do the same thing, we would have a sequence of blocks as before, with at the end fixed with the extra vertices, same computations as before. The diameter is the number of columns divided by how many times delta fits in the number of vertices times n over delta plus big O1. Can we have a good enough block? For the 5 colorable case, 4 divides delta now, because I don't want to get into technical details, we actually found this. So the blocks, every third column has a single vertex. Then 2 consecutive blocks in between have a total number of 5 clumps. Each clump has delta over 4 vertices. I have a little minus 1 here as before. That takes care of this extra edge. And 4, 1, 3, 2, 2, 3, 1, 4. These are the numbers. And if you work this out, it's the diameter of this graph is 13n over 5 delta plus 3. So the constant that you can work with is 13 over 5, which is 3 minus 2 over 5. Again, we can't skip that little bit that they conjectured. And to cut the long story short, we can generalize these examples in such a way that we create a block with 6r minus 5 columns. The number of vertices is 2r minus 1 delta plus 2r minus 3. And that gives us a constant 3 minus 2 over 2r minus 1 times n over delta. As best possible, that works for all delta. This is the actual quantity that we get with equality. And this is the counterexample for the Erdős, Pach, Pollack, Tuza conjecture when delta is big enough. So these examples shows that you can't shave off that extra thing when delta is big enough. If delta is smaller than this quantity, Erdős, Pach, Pollack, and Tuza might still be right. So how does this block look like? When 2r minus 2 divides delta, we have the number of columns in the clumps in the columns as before. Every third column has a single clump. In between the two clumps, columns, the number of clumps add up to 2r minus 1. Starting with 2r minus 2, 1. First column clumps, number of clumps decrease to 1. Second column number of clumps increase. There are a total of 6r minus 5 columns. I'm just writing down what I said before. All edges within a layer and between consecutive layers are there. The clump sizes are 1 for this single vertex for every third columns, and the other guys have delta over 2r minus 2 vertices. That's why I need the divisibility condition. And everything works out. This is a schematic view of what we have. What happens when there is no divisibility? Pretty much the same thing is going on, except I need to put in floors and ceilings over the delta over 2r minus 2 because that's not an integer. So if I tell you in every column how many ceilings are there, we know what's going on, and I can tell you. Let's not even look at those formulas because they are ugly. What happens here that in the middle, around this single vertex, because this is a single vertex, I have d is the remainder when you divide delta with 2r minus 2. I have d over 2 ceiling and d over 2 floor ceilings in the clumps. So this guy still has as many neighbors as it has to have. And then I put in every column here as many of the d minus 1 ceilings as I possibly can. And on the other side, I put enough ceilings that I have a total number of d, and that again makes sure that everything is fine. And if you work out the computations, the number of vertices are exactly as I claimed. And everything works out fine. Oh, something disappeared. Okay. So we need to update the conjecture. For every k at least 3 and delta bigger than or equal to 3k over 2, I told you earlier why I need to have that, because otherwise the previous bound is better. If G doesn't have a complete graph of size k plus 1, or G is k-colorable, that's the weaker version, graph of order n, minimum degree delta, then the diameter is at most 3 minus 2 over k times n over delta plus big O1. If this conjecture is true, it's best possible by your examples. Now, if delta is less than 3k over 2, then the known upper bound of 3n over delta plus 1 on the diameter is better than this, so there is no reason to worry about it. If k is even, then 3r minus 1 divides delta. This conjecture is the exact same thing as the original one, and their construction shows it's best possible. Otherwise, all construction shows, or as I mentioned earlier for Anton's question, their construction can be modified similarly. So that would show too that this is the best possible that works for all delta simultaneously in this form, c times n over delta. Otherwise, you could have something like constant times n over constant times delta plus another constant where the c works out to be the same. When k is odd, or construction shows that this is best possible that works for all delta simultaneously in this form. And the Erdős, Pach, Pollack, Tuza may still be true in the range where the divisibility condition can be satisfied and delta is smaller than that quantity that we had earlier. So far so good. We have a modified conjecture. We have structures that show that if true, it's best possible. In fact, in the case of k equal to 4, we actually know that this is true. So what can we do in terms of upper bounds? So I'm going to now shy away from maximum clique size. we consider k-colorable graphs because we can use clump graphs. And clump graphs are much easier to handle. So we consider H maximal graph, fix a k-coloration, vertex V of maximum eccentricity, Li is a set of vertices at distance I. We define by the clump graph by replacing vertices of the same color in the same distance clump with a single weighted vertex. Ci is the number of colors used in the IS distance class of the fixed k-coloration that we have. And it also happens to be the number of vertices in the clump graph. And Li is the number of vertices in the original graph, also the sum of the weights in that column in the clump graph. So we can show the following. If you take any k-colorable connected graph of order n diameter d and minimum degree at least delta, there is a connected k-colored graph G of the same parameters where the following is true. The first and the last layer contains a single vertex. And if it's not the last layer and you have just one color, not just one vertex, one color in a layer, in a distance class, then the next layer contains at most k-1 colors. The number of colors used in two consecutive columns is the maximum possible. So it's either k or it's the sum of the number of columns in the two consecutive columns. But what I mean by it, that if you look at Li union Li-1 as a coloration, colors are only repeated if Ci plus Ci plus 1 is bigger than k. And if a column uses k colors, then the next column doesn't use just one color. Now, if you think about what this means for a second, the first two are obvious. The last one requires a bit more work. You have to actually rearrange your graph truly, because in the previous ones you don't really. But I don't want to go through that because that's just case analysis and, you know, oh, if this plus this is less than that, then I do this. And so it's not that interesting, but this is something that we really needed to use for what we have. And clump graphs satisfying these properties we are going to call canonical. And it's enough to restrict ourselves to these graphs. So we have used the linear programming approach with the dual to do something. So we slightly modify our questions. The previous question was fix the number of vertices, fix k, fix delta. What's the maximum diameter? K is the number of colors, delta is the minimum degree. So I want to maximize D, capital D. Now I'm going to turn this around. I fix capital D, the diameter, delta, minimum degree, k, the number of colors. How small can n be? That there are connected k-colorable graphs of minimum degree at least delta and diameter d. This is the same question. Just look at it differently. And this can be phrased as an integer linear programming program. You take the family of unweighted canonical clump graphs that arise from these guys. So forget about the weighting, but take everything that can possibly come from these graphs. And you want to figure out what's the minimum weighting that you can put on this, where the weighting is integer weights. Every vertex in the clump graph gets a positive weight because I want to know how many vertices are in that thing and something needs to be there. The goal is minimize the total number of vertices, which is the sum of the weights, subject to the condition that everybody must have at least delta neighbors. So every vertex in the clump graph, if you add the weight over its neighbors, it's at least delta. Okay, fine. This is a linear programming problem. Let's even ignore the integer part now. We can consider the dual. The constant terms are all delta. The optimization function have all ones in the coefficient. And the matrix is the adjacency matrix, which if you transpose, you get the adjacency matrix back. So the dual program looks like this. Maximize delta times the sum of the dual weights, subject to the condition that for every vertex, the sum of its neighbors is at most 1. Fine. So the theorem is if there are constants u and c such that for all d and delta and all h in the canonical graphs, the optimum of the dual program is at least u times d delta d plus c times delta. Then for any graph, we have that the diameter is at most 1 over u times n over delta plus c prime for some other constant c prime. And this is the trivial direction of the duality. So I'm not even going through this because anybody who has seen this problem in general for the linear programming knows that this works, and that actually gives what we want. So this rephrases my problem. Use dual weights in such a way that the sum of the weights of the neighbors is at most 1. Look at find an upper bound on the total sum of the weights of the neighbors, and that gives you your constant in terms of 1 over u here. And that's what we are going to do. And using this, we have managed to prove that if you have a k-colorable connected graph of minimum degree at this delta, then the diameter is at most 3 minus 1 over k minus 1 times n over delta plus big O 1. This is not what we would want, because we would want 3 minus 2 over k, but this is at least in the right order, so to speak. And let me go back. So this is something that is new. This is something that we haven't known. When k equals to 4, this doesn't give us much because we already knew that the 3 minus 2 force is fine. And when k equals to 3, that is actually gives us the 3 minus 2 force upper bound, which we already know for free colorable graphs because free colorable graphs are 4 colorable. But for every bigger k, this gives something new. And as 1 over k minus 1 is between 1 over k and 2 over k, the improvement is in the right order. And what I have said earlier, it's enough to assign dual weights such that every layer has total weight k minus 1 over 3k minus 1, because then the 1 over u that I had before is going to be 3k minus 4 over k minus 1, and that works out to be exactly what I want. And that's what we do. We take an unweighted canonical graph with layers L0, L1, LD. If the number of colors is less than k, we assign dual weight k minus 1 over 3k minus 4 times the number of colors. So the total weight is going to be k minus 1 over 3k minus 4. And that in particular means that the weight of every layer, every vertex in the layer has weight at least 1 over 3k minus 4, because I'm dividing with something that's at most k minus 1. If I have k color, I have to work a teeny bit harder. So I divide my vertices into 2 sets. Xi is those guys who are adjacent to all of the 2 neighboring, all vertices in the 2 neighboring column, and yi is the rest. I assign dual weight 1 over 3k minus 4 to vertices of xi, and this quantity to vertices of yi. This quantity works because then the total weight of the layer is going to be 1 over 3k minus 4. That's how I chose this. Vertices in xi get weight 1 over 3k minus 4. Not everybody belongs to xi because the column has all the colors, and some of the colors must repeat on the 2 sides. So I'm dividing with a non-zero quantity here. And vertices of yi get weight at least half of this much. So why is this good? This was supposed to move, something got messed up, sorry. So for convenience, I'm going to set L minus 1 and LD plus 1, which don't exist, to empty set. A vertex which in the IS layer has only neighbors in the I minus for the IS and the I plus first label, except itself. The 3 layers together have at most 3 times k minus 1 over 3k minus 4 weight. If the dual weight of x was at least 1 over 3k minus 4, then since he's not adjacent to himself, the total weight of the neighbors is at most 1. So everything is fine. This happens when we are in a column that has less than k-colors, or if we are in a column that has k-colors, but the vertex one is in xi, so the only thing I have to worry about what happens when x is in yi. But then he is not adjacent to at least one more vertex in the neighboring columns. I'm going to call that guy y. And x and y both have at least half of 1 over 3k minus 4 weights. So again, everything works out just fine. So this weighting works, and this proves my theorem. Okay, let me see how much time I have left. Okay. So now all we have left is we have proved a new upper bound for every k-colorable graph, k at least 5. We already knew what the truth is for k equals to 4. For free colorable graphs, this didn't give us anything new. So we started to work on that too, because it's nice to have new results when you can have it. And we have managed to prove that for every free colorable graph G of order n and minimum degree at least 1 connected, the diameter is at most 57 over 23 n over delta plus big O1. In particular, if in the canonical column graph of G, the only columns, the only layers that have just single color are the first and the last one, then we actually can prove the bound that we think is correct, 3 minus 2/3. This is actually annoying, because the only example we know that gets close to this upper bound is full of layers which have just a single color. If you remember, every third column had a single color. So the example that shows that this might be sharp, the only thing that we are aware of violates this condition, but we can only show this when we do not have any single layer color except for the first and last one. And just for comparison, 7/3 is the one that we are shooting for, 5/2 is the one that we know, and 57 over 23 is what we have managed to prove. You can see how much in between it is. And we use inclusion on exclusion, and we obtain inequalities of this type. They are not hard, they are just work. And I'm going to go through this. We obtain inequalities of this type. We introduce variables. This is going to be, again, another linear programming approach. x1, x2, x3. x1 is going to be the fraction of the vertices that lie in single color layers. x2 is going to be a fraction of the vertices that lie in two color layers with single colors on both sides. x3 is going to be fraction of vertices that lie in two color neighbors with one single color on one side and not a single color on the other side. x1 plus x2 plus x3 is at most 1. x4 is d times delta over n. I want d to be at most constant times n over delta, so x4 will correspond to my constant. And x5 is s delta over n, when s is a particular kind of column. We can show a couple of inequalities of this type, and this would be a linear programming, complete linear programming problem, except I have this big O delta over n instead of constants. So we have this problem. I have 5 variables, maximize x4 subject to this type of condition. If I wouldn't have that big O delta over n term, then I would have a nice linear programming program I know how to solve. Routine arguments based on duality show that the optimum in the first problem is the optimum in the second problem plus big O delta over n. Which means that it's still enough to show the second problem. You flip out your favorite linear programming solver and you get the constant that I told you earlier. So what are the problems left? Well, what is the actual truth? We have an upper bound, but we think it should be something better. We don't know. And oh, this doesn't even touch the original problem. It's related, but being k-colorable is a whole lot weaker than not having a clique of size k plus 1. And one thing that we were wondering about, the examples that we found that got near the conjecture bound are all periodic. Is it true that if something gets near enough to the bound, whatever is the near enough that you want to define, you will get something that's periodic or very close to being periodic. And that's all I wanted to say. I think I'm still within time. Thank you very much.
Thank you very much. Let's thank the speaker. Are there any questions? Well, I have a question actually. So your results are for graphs that with chromatic number at most case in these upper bounds. Is it possible to say something about graphs whose fractional chromatic number is at most k, using similar techniques maybe?
I haven't thought about that one, but I mean, with the upper bounds, we use a lot of linear programming techniques. Mm-hmm. The ones that well, actually,
yeah, that's why I'm asking.
I would have to, I haven't thought about it. I would have to think over my original integer programming thing, whether it translates to everything, because then the upper bound works for
right, which is something in between, I guess.
Yeah, so I would have to think of, but it's possible that something is related, because the technique that we are using are linear programming, and you can view the fractional problem as a linear programming thing. So it actually makes sense, your question. We just haven't thought about it. It's a very natural one, actually. I'm ashamed that we haven't thought about it.
Are there any more questions?
However, so the theorem where you have the 3 minus 1 over k on the bound, does the weights come from the solver, or is it just
3 minus 1 over k minus 1?
Yeah, that theorem.
No, we have a dual weighting that gives that bound. So that's not linear programming solver. That's just the dual approach.
The dual approach, and then just assign these weights, and then it works.
You assign the weight the way I said, and everything works out.
Okay.
And the thing is that the problem with doing anything better over there, that you would need to know a lot more about the structure. And I tried, but and I'm not saying you can't, but you probably have to put a lot more in terms of the properties of your canonical graph that you can use there. And you have to figure out what that lot more is, and we haven't yet.
Okay. Yeah.
So for example, if we wanted to do kind of a thing similar to what you did with k equals 3, but say for k equals 5 to get some nicer bound, in principle, you're saying it is possible to try to get enough inequalities to run a.
It's possible, and I'm not even saying that the k equal to 3 case you can't do it perfectly. If you figure out how to do the things. We really tried with the free colorable case, actually, and we just gave up at a certain point. And okay, this is beyond 2.5. This is just too hard to figure out how to get lower than this. So,
I see. And the difficulty is coming up with these inequalities that you had to.
Yeah, that actually work out fine.
I see. Yeah. Any more questions? Comments? All right. If there are no more questions, then let us thank Éva again. And our speaker next week will be Ruth Luo from UCSD.